Okay, our next limit equilibrium technique I want to talk about is the log spiral technique. With the log spiral technique, we assume that the shape of the failure surface is in the shape of a log spiral. Not only that, but it's a very specially formulated log spiral. So we choose a center point and then a point on the top, the head of the slope where the surface starts. And then as theta increases in this direction, the radius of this, the distance from the center to the failure surface as you go around it increases. That's the definition of a log spiral. As you rotate, the radius increases. And that is defined by this equation. R is equal to R naught, this initial radius, times e to the theta tan phi d, where tan phi d is the developed or mobilized friction angle. Now, why on earth would we use that shape? Well, it turns out that it leads to some very unique, a very unique kind of solution for this. Now, remember from our earlier discussion that we can express the mobilized shear force along a slope as the shear strength divided by the factor of safety, and so we get the mobilized cohesion, and then the mobilized friction is tan phi over the factor of safety. And so this equation for the log spiral uses this mobilized friction over here. All right, now why do we do that? If we sum moments about the center of the spiral, so we're going to move along the shape of this log spiral, and we're going to sum moments about the center. If you take the normal force that's acting perpendicular to that surface at any point, and then the friction, the resistance is equal to sigma tan phi mobilized. This is not the cohesion, but the mobilized friction. The resultant of those two, because of the shape of this surface, ends up going right through the center of the spiral. So if you sum moments, the moments due to these two things cancel. And we're left with the moment due to the weight of the soil mass. So it's not shown here, but if you were to compute the weight of the soil mass, find the centroid, there would be a weight term, and you'd have a moment based on the distance of that from the center. And then there's a moment due to mobilized cohesion. So that would be cohesion that acts parallel to the surface, along the surface. And so even though there's friction here, the moments end up being, or the equations end up simplifying to a moment due to the soil mass and a moment due to the mobilized cohesion. So we have one equation and one unknown. Now, so simple equation, right? Well, the problem is the geometry of this failure surface depends on the mobilized friction angle, which is a function of the factor of safety. So you have to make a guess at the factor of safety, generate a surface, calculate the factor of safety, make another guess, and keep iterating until you get a match. So it's something that it's difficult to do by hand, but you can write software to do it fairly easily. So it does achieve a statically determinate solution by virtue of the shape of the slope. It explicitly satisfies moment equilibrium, implicitly satisfies force equilibrium. So it's what we would call a complete equilibrium procedure. And it turns out it's relatively accurate compared to a lot of the solution techniques we'll see. So in summary, it's a really good procedure for homogeneous slopes. This doesn't work when you have multiple materials. It's tough to solve by hand, but works well with simple programs. Also, later this semester, we're going to look at slope stability charts. For simple slopes, there's a way to look up the factor of safety from a chart. And those charts are often generated using solutions from a log spiral technique.